Hello, this will be a demonstration of proposition 36 from book 9 of Euclid's Elements, which says that if numbers be in double proportion beginning from the unit, and the sum of them be a prime number, then the product of this prime sum and the last number so produced will be a perfect number. This is the first and only mention of perfect numbers in the 3 books of Euclid's number theory, so let's review it while we're here. A perfect number, as defined at the beginning of book 7, is any number which is equal to the sum of its parts. An example of such a perfect number would be the number 6. In fact, it is the least perfect number, because its parts are 1, 2, and 3, and the sum of 1, 2, and 3 makes the number 6. So 6 is a perfect number. That's what we call it. Other examples of such numbers would be 28, 496, and 8,128. They're not only important numbers, but they're also quite beautiful, that there are some numbers which are equal to the sum of their parts. So this proposition about producing perfect numbers is fittingly placed at the end of Euclid's number theory. We're given numbers which are in double proportion, beginning from the unit. So we start with the unit, we double it to get the dyad A, we double A to get B, double B to get C, and double C to get the last number D. We're also going to take their sum and call that the number E, and E will be prime. This sum, we're going to extend this double proportion out until this number E is prime. So the prime number E is equal to the unit plus the dyad A plus B plus C plus D. We're also going to take the product of this prime sum and the last number D. So E multiplied by D makes the number FG. Then, what we want to prove in this proposition, that the number FG is a perfect number, that it is equal to the sum of its parts. We're going to begin by creating 3 numbers, H, K, L, and M, which are in double proportion, beginning not from the unit, but from our sum E. So E doubled will make HK, HK doubled will make L, and L doubled will make M. We're also going to make the 2 numbers, HN and FO, we're going to cut them off equal to E. So we're going to cut off from the number HK, the number HN equal to E. And we're going to cut off from our number FG, the number FO equal to E. Now, because our given continued proportion is a double proportion, and the proportion we just made of E, HK, L, and M is also a double proportion, they're therefore in the same ratio as each other. That is to say, the dyad A is to the number B, just as E is to K, B is to C, just as HK is to L, and C is to D, just as L is to M. So these 2 continued proportions are equal to each other, and furthermore, they are equal in multitude. That is to say, they have the same number of terms. So we can then say, by proposition 714, that xi quali, the dyad A, is to the number D, just as the number E is to the number M. But this then means, by proposition 719, that the product of D and E, which is the number Fg, is equal to the product of the dyad A and the number M, which of course means that our dyad A and our number M both measure this number Fg. Now, in a similar way, we can prove that B, C, HK, and LM, all of those numbers also measure the number Fg. We would prove that like this. We would have B, C, and D form a continued proportion in the same ratio as E, HK, and L. Furthermore, they are equal in terms, so we can then say xi quali, that B is to D, just as E is to L, so that D times E, that is the number Fg, is equal to the product of B and L, so that B and L both measure Fg, and similarly, we would prove this for C and HK. So all of these numbers measure the number Fg. Now, because the number Fg is equal to the product of the dyad A and the number M, it means that our number Fg is equal to exactly twice M. Fg is double M. So we can actually put it at the end of the continued proportion we made in our first step, because m doubled makes fg. So in total, we would have a continued proportion in double proportion of e, hk, l, n, and fg, because each term is equal to twice the previous one. Now, because the number nk is equal to hk minus e, you remember we made hn equal to e. So if nk is equal to hk minus hn, and hn is equal to e, nk is equal to hk minus e. And similarly, our number og is equal to fg minus fo, and because fo we made equal to our number e, og is therefore also fg minus e. We can then say, by proposition 935, that we have this continued proportion from E, HK, L, N, and FG. And what 935 tells us is that the second number minus the first number is to the first number, just as the last number minus the first number is to the sum of all those numbers up to the last one. That is to say, for our particular example, that NK is to E, just as OG is to the sum of E, HK, L, and M. Now, we know HK is double E, because that's how we made HK to be in double proportion beginning from E. And because HK is the second number, it is therefore twice E. So if we subtract a number equal to E from twice E, we just get E back. And that would mean for us that NK is equal to E, because we subtracted from HK, which is twice E, the number HN, which is equal to E. So the remainder NK is also going to be equal to E. But we know, this is a property of numbers, that if four numbers are proportional, and the first is equal to the second, the third is also equal to the fourth. So that, because NK is equal to E, and we know NK is to E, just as OG is to E plus HK plus L plus M, we then also know, again by this property of numbers, that the number OG is equal to E plus HK plus L plus M. Now, the number FO we made equal to the number E. And furthermore, we know from our given that E is equal to the sum of A, B, C, and D. So if we add OG and FO together, what we're going to get is that the number FG is equal to A plus B plus C plus D plus E plus HK plus L plus M. So we see that this number FG is a sum of its parts. But we have yet to prove that these numbers A, B, C, D, E, H, K, L, and M are all of its parts. So we have yet to prove that FG is a perfect number. But if we can prove that there is no number besides A, B, C, D, E, H, K, L, and M which measure the number FG, then we will have proven that FG is a perfect number. Now you notice the rest of my board is blank. So I plan to cut the video here and move on to the second part of the proposition, where we prove that FG is only measured, its only parts are these numbers A, B, C, D, E, H, K, L, and M, so that FG is a perfect number, and that we will therefore be done with the proposition. So I'll end this part of the video here and move on to demonstrating the second part of proposition 936. Now, if these are not the only numbers which measure FG, then there will be some number P which measures FG and is not the same as the unit, the dyad A, B, C, D, E, H, K, L, or M. So if these are not the only numbers which measure FG, there will be some number P which is not equal to them, which also measures FG. Now because number P measures the number FG, there will be some number according to which it measures it. So we're going to call that the number Q. Q will be the number according to which P measures FG, or in other words, the product of P and Q is the number FG. But we also know that the product of E and D is the number FG. We stated that in our given. So these two products are equal to the same number. Common notion 1 tells us that they are the same with one another, so that the product of E and D is equal to the product of P and Q. And we know from proposition 719 that if a product be equal to a product, the four numbers are proportional. So that because the product of E and D is equal to the product of P and Q, E is to Q just as P is to D. Now we know the number P does not measure the number D, for we know that the number D is measured only by A, B, and C. We know this from proposition 913, because the number D was made such that beginning from the unit, we arrive at the number D through a continual proportion which begins at the unit. So proposition 913 tells us that this last number D is only measured by those which come before it, in this case A, B, and C. But because we know the number P is not equal to A, B, or C, we know that the number P does not measure the number D, which then means by the definition of proportionality, because P is to D just as E is to Q, and the number P does not measure the number D, the number E does not measure the number Q either. Now, because the number E is prime, we know that E and Q are prime to each other. For proposition 729 says that any prime number is prime to any number which it does not measure. So that because the prime number E does not measure the number Q, our two numbers E and Q are prime to each other. Which then means from proposition 721 that they are the least numbers in their ratio. Which then means from proposition 720 that because E is to Q, and just as P is to D, and E and Q are least, E measures P the same number of times that Q measures D. We don't care about all that though, we just care about the fact that Q measures D at all. Because if the number Q measures the number D, as we have just shown, Q is therefore equal to one of the numbers A, B, or C. Because we know that A, B, and C are the only numbers which measure the number D, so any number which measures D has to be equal to one of them. For right now, we're just going to say that Q is equal to B, but we can do this exact same logic with Q being equal to the dyad A or Q being equal to the number C. But for right now, we're going to let the number Q be equal to the number B. Now, because B, C, and D are in a continual proportion in the same ratio as E, H, K, and L, we know that from our given, we made H, K, and L in double proportion starting from E, and we made C and D in double proportion starting from B. Therefore, these two continual proportions are in the same ratio, which then means xi quali, that B is to D just as E is to L. That's proposition 714. Because B is to C just as E is to HK, and C is to D just as HK is to L, xi quali, by proposition 714, B is to D just as E is to L. Which then means, by proposition 719, that the product of the extremes B and L is equal to the product of the means D and E. But we also know that the product of E and D is equal to the product of Q and P. We had shown that in our 10th step. So we have two products which are equal to the same product. Common notion 1 tells us that they are the same with one another, so that the product of Q and P is equal to the product of B and L, which then means, again by proposition 719, that Q is to B just as L is to P. But the number Q is equal to the number B. Therefore, by a property of numbers, L is equal to P as well. But we know from our 8th step that L is not equal to P because P is not the same with L. So, if there is some number besides the unit, the dyad A, B, C, D, E, H, K, L, and M, if there is some number other than these, which measures the number Fg, then the same number L will be both equal to and not equal to the same number P, which is obviously absurd. And because we can prove a similar absurdity arises when Q is equal to the dyad A or Q is equal to the number C, we can then conclude that the number Fg is measured only by the unit, the dyad A, B, C, D, E, H, K, L, and M. But we had also shown in our 7th step at the end of the previous part of this video that the number Fg is the sum of these numbers. Fg is equal to the sum of the unit, the dyad A, B, C, D, E, H, K, L, and M. And because it is only measured by these numbers as well, according to definition 722, our number FG is a perfect number, which is what we set out to prove, which means we're done with the proposition, therefore, etc., QED. An absolutely beautiful proposition that caps off Euclid's number theory perfectly. It ties in so much of book 7, so much of book 8, and so much of book 9 to get perfect numbers. I mean, how amazing is that? We're ending the number theory on literal perfect numbers. It's just beautiful, and this proposition is amazing. I do want to go over it a little briefly with modern notation, because this proposition is still used nowadays. It's still relevant. We still talk about perfect numbers, and we still generate them this way. So let's just start like this. We know that our given proportion begins from the unit and is in double proportion. So it's going to be of the form 1, next number will be 2, then 2 squared, and then we'll continue this on and on to what I'll say is 2 to the n minus 1. And you might be asking, why don't I just do 2 to the n for the last term? You'll see why I don't do that. Now, what this proposition says is that if the sum of all of these numbers makes a prime number, then this sum multiplied by this last number makes a perfect number. So we know that, at least this is something that I wrote at the end of the previous video, that the notation for this is just S of S sub n. So the sum of all the terms up to the n minus 1 term would be what it is here, because we ended on the n minus 1 term. Again, we'll get into why I didn't end on the nth term. So what this proposition is saying is if S sub n minus 1 is prime, then S sub n minus 1 multiplied by our last number, which here is 2 to the power of n minus 1, is perfect. That's what this proposition tells us. It tells us that if the sum of all these terms in this double proportion beginning from the unit is a prime number, then this sum multiplied by the last number makes a perfect number. Now, you'll also remember in proposition 935, the upshot, the modern upshot of that proposition is a formula for the sum of a continued proportion up to any term. We revealed that that formula was that we know that Sn is equal to the first term multiplied by the next term minus the first term divided by the second term also minus the first term. So we can actually turn this sum, this S sub n minus 1, into this notation. What that would mean for us here is that S sub n minus 1 equals, well, it would equal our first term, which is just the number 1, multiplied by the next term, which if we're ending on the 2 to the n minus 1 term, our next term is just going to be 2 to the n. I'll write this a little bit bigger just because this is really important. So we would write this as our first term 1 multiplied by the next term, were we to continue this proportion by another term. And if we were to do that, we would get onto the 2 to the power of n term, like this, minus our first term, which is again 1, divided by our second term 2, minus our first term 1. Now, you'll notice a lot of this just cancels out. If we multiply 1 by anything, we'll just get that same number. And 2 minus 1 is just 1. So this sum, the sum of all the terms in this double proportion up to the n minus 1th term is just equal to 2 to the n minus 1. So S sub n minus 1 is equal to 2 to the n minus 1. So if we were to substitute that in for our statement here, that s sub n minus 1 multiplied by 2 to the n minus 1 is perfect. What that would mean for us is that 2 to the n minus 1, if this is prime, if 2 to the n minus 1 is prime, then 2 to the n minus 1 multiplied by 2 to the n minus 1 is perfect. That's what this proposition tells us. It tells us that if 2 to the n minus 1 is a prime number, then 2 to the n minus 1 multiplied by 2 to the n minus 1 is a perfect number. So we can actually generate the first 4 perfect numbers in this way. And I'll end the video by doing just that. We'll get 4 perfect numbers. So if we want this 2 to the n minus 1 term, which I will say just very briefly, if this is a prime number, we call these Mersenne primes, named after someone named Mersenne who did a lot of work with such prime numbers. Mersenne primes are any numbers which are any prime numbers which are 1 less than a power of 2. So 2 to the n minus 1 is a Mersenne prime. So that's cool. We're working with Mersenne primes. They're still used nowadays. In fact, I think by now the largest prime number we've ever found is in this form of 2 to the n minus 1. So Mersenne numbers pop up all over the place. And how beautiful is it that they show up in perfect numbers? So if we were to get our perfect numbers, our first 6 ones, excluding the unit, I mean, 1 is obviously a perfect number, but it's not a number, so it can't be a perfect number. So we're just going to start by taking, if n is 2, then 2 to the 2 minus 1. If we plug in 2 for n, this equals 3, which is prime. So what that tells us is that if we do 3, which is our 2 to the n minus 1 term, multiplied by 2 to the n minus 1, and if we do that, if we plug in 2 for n here, 2 to the n minus 1 is just 2 to the 1. So 3 times 2 is a perfect number. And we can verify that. 6 is, in fact, a perfect number. It is equal to 1 plus 2 plus 3. It is equal to the sum of its parts. So the first time we use this formula, it works. Now, the next one would be where n is 3. If n is equal to 3, the corresponding Mersenne prime of 2 to the n minus 1 equals 7, which is prime. So that tells us then that 7, which is our 2 to the n, that whole minus 1, multiplied by our 2 to the n minus 1 term is a perfect number. Now, if n is 3, our 2 to the n minus 1 term is just 2 to the 3 minus 1, 2 to the 2, which is 4. So that tells us that 7 times 4, which equals 28, is perfect. And we can verify that as well. 28 is the sum of 1, 2, 4, 7, and 14. So 28 is, in fact, a perfect number. And we have just gotten our second perfect number with this formula. Now, the next two I'll go through very briefly, just because I don't know the factors of them. The next two would be where n equals 5. Our corresponding Mersenne prime would be 2 to the 5 minus 1, which equals 31, which is prime. So that tells us that 31 multiplied by our 2 to the n minus 1 term, which here is 2 to the 4, which is 16. This equals 496. This is perfect. 496 is our third perfect number. The last one I'll talk about is when n equals 7. Now, if n equals 7, our corresponding Mersenne prime of 2 to the 7 minus 1 equals 127, which is prime. So this proposition, again, is going to tell us that if we take 127 multiplied by 2 to the n minus 1, which here is going to be 64, because it's 2 to the 7 minus 1, or 2 to the 6, 127 multiplied by 64 equals 8,128, which is perfect. So we have also found our fourth perfect number, and we could keep going like this. In fact, perfect numbers are still being found to this day. couple things I want to mention before I end this part of the video here. One, this is not, or we have yet to prove that all perfect numbers are of this form of a Mersenne prime multiplied by a 2 to the n minus 1. All this proposition tells us is that you can get perfect numbers this way, not that all perfect numbers are of this form, which is why actually we don't know if there are any odd perfect numbers. All the perfect numbers we found so far are even, but we have yet to know if there are any odd perfect numbers, but we have yet to disprove that odd perfect numbers are impossible. Another thing I want to mention about this is, well, I actually forgot. So I'll just talk for a little bit about just how beautiful this is. I mean, I really do want to stress that. There's such a beautiful relationship between the powers of 2 and perfect numbers. I mean, it's amazing. And it's amazing that Euclid found this. This is beautiful. This is amazing, which makes this a really bittersweet ending, because I've been doing number theory, or we've been doing number theory, really, because this is you and us. We've been doing number theory for so long. It's been the last 3 books, and I think I started recording these in like April. So I've been doing these for about half a year, 6 months. And yeah, at points this was kind of hard to get to. I admit that Euclid's number theory is not the most riveting while you're doing it. But by the time you get to the end of it, at least I'm sad that it's over. I'm sad that this is the last proposition. We end on something so beautiful, that you can get something this beautiful out of number theory, out of just working with numbers. I mean, that's amazing. And the result that we get, I mean, it's an amazing result, that a relationship between the powers of 2 prime numbers and perfect numbers. I mean, that's amazing. That's everything cool about math right there in this one proposition. It's just so awesome. So not only am I happy to be ending Euclid's number theory on this one, by the time this video goes up, it will be the birthday of the channel. I started making videos, in fact, I started up this channel on October 20th of 2021. And when I record this and when it goes up, it'll be October 20th, 2022. So this is the 1-year anniversary of the channel. I've been doing this for a whole year, which is why I really wanted to get to this one, which is why I've been going at such a fast pace, because I wanted to get to something this beautiful, so beautiful, on the channel's anniversary. And because it is the 1-year anniversary of the channel, it is the channel's birthday, I really just want to say thank you to all of you who support me for this. This is a one-man operation. I get help from my friends here, because they know their stuff as well, and I get help from, obviously, commentators on Euclid and from Euclid himself. But for the most part, this is just me. I go into this room, I set up my phone on a tripod, on a chair, on a desk, and I just record videos like this all alone. And so I just want to say thank you for supporting this. It really means a lot to me. And I'm going to deliver on these last 4 books. Book 10 is the hardest book of the elements, and it's not close. And books 11, 12, and 13 are about solid geometry, and they end with constructions of the Platonic solids. So I really do want to deliver on those, and I'm very excited to continue working on this channel after its first year. This first year has actually been quite good for the channel. I think that this operation has been a success, so I have no plans on stopping it until I get to the end of the elements, and who knows, maybe I'll even do more after Euclid. So that's all I've got to say about this proposition. Again, thank you so much for sticking with me. Yeah, I'm gonna tear up. I'm going to end the video here because this is all I have to say about this proposition and about this day and about this channel. So I'll end the video here and move on to proposition 10.1.